Okay, so this is the first AP exam review. This is on everything that is related to limits, continuity, asymptotes, holes, something being differentiable. The main topic here is going to be limits, but it is going to cover some other little details that seem that they could be nitpicky, but that tend to show up. So we need to make sure that we know how to handle these. At any point, I'm teaching to an empty classroom. So at any point when you're going through this video, you need to slow it down, pause it, chew on something, think about it. Please do so. Don't just go at the speed of the video. I will go through problems throughout all 7 practice tests, and then you will have an assignment of problems to do on your own, and then the next day we'll go over those problems, and then we will start another topic. So this needs to be something that you chew on for as long as you need each day so that it sinks in, because we have a lot of topics to cover. Okay, the first thing I want you to do is get your formula sheet out. Every video is going to focus on a specific part of the formula sheet. You do not get this formula sheet on the exam, but I wanted you to have something throughout the semester to kind of stare at. Okay, so some things to remember, just some general topics that we're going to be talking about. You need to know what continuous means. Continuous means that it's fluid, it doesn't stop, doesn't have any holes, it doesn't have any asymptotes, it's very well behaved. So I have this example off to the side, and you can see that it is continuous until it gets to here, and then this is discontinuous, and then it's continuous to here, and then this is discontinuous to here, then that's discontinuous to there. So the function f, the whole function from here to here, is not continuous. It has 2 holes. One of them is right here, and one of them is right here. This one is removable. No, not removable, because it's not plugged in. The hole doesn't, the dot doesn't plug the hole. Sometimes it'll have a hole, and then the function will say, oh, okay, at f of -1, we're going to let it equal 1. So when x is -1, if we plugged it in at 1, that would be removable. But because this one is defined way up here at 2, this one is a complete jump, and this one is a hole. You also have asymptotes. And remember to find vertical asymptotes. You set the bottom equal to 0 and solve. We're going to be doing that. Vertical asymptote, let's say if you have an asymptote here, you can have a function that looks like this. Let's say the asymptote happens at 2. If we were talking about a limit, as x approaches 2, well, as we approach 2 from the right and as we approach 2 from the left, we're headed to 2 different directions. One's negative infinity, one's positive infinity. So that limit would not exist. If you had, and I think we called them kissing functions, where that did this, then the limit as x approaches 2 would be positive infinity because it's headed to the same place on both sides. So just make sure you understand how asymptotes play a role in limits. And again, those problems are going to pop up today. Differentiable just means no sharp turns, and it doesn't stop. So this function would not be differentiable here, 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 or here. It has to be fluid and continuous and no sharp turns. Okay. The other thing that you need to remember from your formula sheet, and I want you to get eyes on this section of your formula sheet. It's on the front page, far left, all the way down. This guy right here is the definition of a derivative. I don't know if you remember, but way back in the day, you had to find, there was a day where we found derivatives using this limit function. And we even talked about that, this actual function a little bit in pre-cal. And it was awful and tedious and very algebra intensive. And then the next day I said, oh, well, there are these rules. And that's when we did the low-d high, high-d low, and the product rule and the chain rule. And we didn't have to do derivatives with this limit function anymore. But he pops up a lot when you're talking about the definition of limits in multiple choice problems. So we need to make sure that we revisit him. He doesn't go as extensive as we went at the beginning, but you do need to make sure that you know who he is. And then there are these guys that we knew once upon a time, but it's been a while, and so we have probably forgotten. So let's take 45 seconds and let's revisit them. So these two are basically the same. You can tell they're the exact same thing except flipped. Notice that all 5 of these limits go to 0. So sine of x over x as x goes to 0 is 1. And then if you flip that, x over sine of x equals 1. All right, stop and memorize that. The limit as x goes to 0 of sine of x over x equals 1. And then you can flip it and get the same thing. Okay, then there's this guy. Again, we're headed to 0. The sine of ax over x is a. So kind of looks like this guy. He's just got an A right there. So instead of a 1, his answer's A. So if I had the limit as x approaches 0 of sine of 3x over x, that would give me a 3. And then sine of ax over sine of bx is going to equal a over b. And again, make sure you see that this has sine on top and bottom. And then you have 1 for cosine, and he's 1 minus cosine x. Make sure you know that that's not cosine x minus 1. It's got to be 1 first. 1 minus cosine x over x, and he equals 0. So the ones with sine in them, and I'm going to focus on this I, equal 1, and the one with cosine in it equals 0. Just make sure that you know the pattern. This is sine of x over x equals 1, sine of ax over x equals a, and sine of ax over sine of bx equals a over b, and 1 minus cosine of x over x. So these two things just need to be the same, whatever it is, and that gives you a 0. Also in doing limits, sometimes when limits would get tricky, instead of using some algebra tricks, we had nice little Hopital. And he said, if I have the limit as x approaches c, so this can be any number, of some function over another function, if you'll take the derivative of the top and the derivative of the bottom. Now notice this is not a low-d high, high-d low. This is not the derivative of this whole thing. It's literally the derivative of the top and the derivative of the bottom separately. And then redo your limit. And sometimes we would go again. We would take the derivative again because if you're headed to 0 and you still have a function that has an x on the bottom and it's going to make the world stop turning by making the denominator 0, then if you'll go again, a lot of times that problem will cancel itself out. With limits, we also talked about as the bottom gets bigger, faster than the top, then the fraction, the bottom of the fraction is going to get bigger, so it's headed to 0. If the top gets bigger, faster than the bottom, then it's headed to infinity or negative infinity, depending on your signs. So all that kind of stuff we're going to talk about today. And again, I'm going to go kind of at a brisk pace with the complete understanding that you're going to pause and write and chew on it as you see fit. Okay, so I'm starting in Barron's, the first practice test. And I'm going to start with number 2. Okay, so if I'm looking at this problem, he is looking like this guy. Okay, so what I have to do is I have to figure out what my f of x is. So this is f of x plus h. It's just stuff, and this is f of something. So the point is, what did you plug into? Well, here's the stuff that got plugged in, and here's some stuff that got plugged in. But the point is, what did it get plugged into? It got plugged into an ln of x. So I can define f of x as ln of x. Okay? Well, what did it plug in? Okay, well, I see my h here, and I see an h here. What did it plug in for both the x's? It plugged in a 2. So what I want is the derivative at 2. Because remember, this is the definition of the derivative. So what you found when you find this, you haven't found the derivative, you found the original function. You found f of x. So I want f prime of 2. So I need the derivative. Okay, so ln of x is the derivative of the of over the of times ln of the base. And my base is e. Ln of e goes to 1. So he's 1 over x. So again, that was derivative of the of over the of times ln of the base. And the ln of the base goes on the bottom with the x. Okay, so I have, that's my derivative. Now I want the derivative at 2. Make sure you understand how I know it's a 2. So then that would just be 1 over 2. So not difficult. Absolutely multiple choice that we can get correct. Okay, now I'm going to jump to number 25. Okay. All right, and this is a great one about asymptotes and limits. Okay, it says the graph of the function y equals f of x is shown above, which is true. Okay, so this says the limit as x approaches 1 of f of x is headed to negative infinity. Well, here's 1. And the limit, not from the right or the left, so I have to look at it from both sides. So it's saying the limit as x approaches 1 from both sides of 1 is headed to negative infinity. Well, that's not true. As I head to 1 from the left, he is headed to negative infinity. But this guy's headed to positive infinity. So he's out. Okay, this is the limit as x is approaching negative infinity. Well, that's that way. It says that my y value should be a plus and a minus 1. Well, that's not true. As my x's head to negative infinity, my y seems to be headed down to 0. So, not true. Okay, this one says that as x heads to negative 2, so here, f of x is headed to 0. And I really think what they're trying to do is trying to get you to look at this negative 2, but this is an x. So here's x is negative 2. Well, from the right and from the left, we are not headed to 0. We're headed to, I don't know, looks like a half maybe. So no, but again, I think they're trying to get you to bite down here that this negative 2 is 0. Now, this would be true if we wrote it this way. The limit as x approaches 0, this is x equals 0, my y value is a negative true. So that would be true if it was written like this. So again, I think they're just trying to confuse you. Okay, D, the limit as x approaches infinity of f of x equals 0. So positive infinity, so we're headed this way. All my x's are getting bigger. And what's my y? What's my graph doing? It's headed to 0. So I'm liking him. I'm just going to check E and make sure he's not true. As x approaches 0, so we've got to be headed here. So from here and from here. It says we're headed to infinity, and that's not true. If I hit 0 from the right and from the left, I'm headed to negative 2, not infinity. So he's out. All right, and then the next one we're going to look at is number 26. Number 26, it says a function f of x equals that for all x's except 1, which makes sense because 1 would make the denominator 0. For the function to be continuous at x equals 1, the value of f of 1 must be, okay, I can't equal 1. X can't equal 1 because it would cause a 0 in the denominator. So I'm going to have a hole there. The way I know I'm going to have a hole there, do y'all remember when you factored this? If they canceled, it was a hole. So I know that I have a hole at x equals 1. Okay, once you take that hole out, my function is now what's left. Okay, what I need to know is I want to know what x needs to be so that the function equals 1. And I know this one's confusing because it just has an x. It's going to end up x equals 1. But let me change something up for you so that it makes sense. Let's say you factored it and you did this and these canceled because bad things happen when x is 1. So I can't be 1. But I'm going to take what's left, set it equal to 1, and solve. And that's what x needs to be to plug that hole. This one was just weird because we were just left with x. So this is that x, that is that 1. Just like this is that x plus 3, and there's that 1. Okay. Now we're going to head over to Barron's 2. Okay. So we're on Barron's 2. We're going to look at number 1 and number 2 first. So let's look at number 1. I want to take the limit as x approaches 2. Well, if you just plug a 2 in, which would be really nice if it works, but if you plug a 2 in, your denominator is going to go to 0, so that's bad. So the question is 2 a whole, because then I can still find the limit, or is 2 an asymptote? So let's look. I can't factor the top. X squared minus 2 are not squares. The bottom is squares, and if I factored the bottom, and I know it's not going to cancel with any of that, then I know that these are going to lead to asymptotes, not a whole, because nothing canceled. So I know I'm going to have an asymptote at plus or minus 2. Well, I'm not interested in the minus 2. I'm interested in the positive 2. So I want to know what happens at positive 2. This is one of those where, let's see, it could do this. And if that's the case, what would be the limit as x approaches 2? It would be headed to infinity. It could do this. If that's the case, as x approaches 2, your limit would be non-existent because they're headed to 2 different infinities. One's positive and one's negative. So non-existent. And then if it did this, as it approached 2, then it would be headed to negative infinity. So those are my 3 options. And then if you look at your 4 choices, infinity and negative infinity are not an option. So we know that it's got to be the one headed up and one headed down, non-existent. And just, you know, for those of you thinking, well, I'll just graph it, if you'll read that dark box above this, it says the use of calculators is not permitted on this part of the exam. So you would have to think through it in that manner. Okay, number 2. All right, as x approaches infinity, well, I have roots, and as x approaches infinity, I have the square root of x over the square root of x, so it seems like they're sort of both headed sort of in the same direction, so I'm going to Hopital this sucker. So I'm going to rewrite this so that I can take the derivative nicely. All right, so if I Hopital, all right, so take the derivative of the top, so pull the 1/2 and then take 1 off as power, and the minus 4 is going to go to 0. That's nice. This positive 4 is going to go to 0. I do still have this negative. Pull the 1/2 out front with the 3. That's going to make that 3/2. Okay, so I'm here. Now, if you sort of are so over-focused, maybe tunnel vision, you might miss the fact that you have an x to the negative 1/2 over an x to the negative 1/2. Both these terms are completely single. You are completely allowed to cancel this. If you wanted to move them because they're negative exponents, you could do that. You can move the bottom one to the top and the top one to the bottom if that makes you feel better. But the point is they still cancel. Again, because they're single. I can't cancel these because they're married. So if these cancel, then all I have is this. Kind of bojangles that. I get a negative 1/3. I don't have any x's, so it doesn't matter what x is approaching. I'm going to be a negative 1/3. So that's a great example of Hopital's rule. Okay, and now we're headed to number 9. Okay. Now, number 9, you might be tempted, because there are h's involved, to do this, and you can do it that way. But because this guy has a root and he does not, I think it would be difficult to see what f of x is. So I wouldn't use the definition of a derivative with a limit on this one. When we went over this way back in the day, I taught you conjugates of the top. It works out really nice. Okay, so when I lobster the top, root of that times root of that is just that. Remember, these are conjugates, so that and that are going to cancel, and then I'm going to have a minus 25. I know my 25s are going to cancel, so I really just have an h. Now, on the bottom, remember the problem is that h is going to 0, and I have a plain old h in the bottom. So the goal, and I think it's very important to stay focused on the goal. The goal is to get rid of that h in the bottom. Well, I have this nice, cute, single h that's very available on the top. If I look at what I'm getting ready to do on the bottom, I don't think it's wise to distribute this h, because again, the goal is to make him go away. So if I leave him out and don't distribute, then he is then available to cancel. So now I have, now Hopital doesn't get you out of doing the limit. I still have an h in here. I still have to do the limit. But now it's not scary to plug a 0 in for h, because it doesn't make the world stop turning. So if I plug a 0 in here, that'd be the square root of 25, which would be 5, and 5 plus 5 would be 10. So the limit as h approaches 0 is 1/10. All right, and now we're going to jump to number 24. Okay, suppose I have a piecewise function. I have 3 different pieces with 3 different intervals. Let's take a second and look at our interval. I got my x squared for x is less than negative 2. And then I pick up with just plain old 4, which is a horizontal line, from negative 2 to 1. Does anybody notice anything about the negative 2? Okay, let's look at the next one. Then I have 6 minus x for x is greater than 1. Do you notice how this one has an equal to and this one doesn't for the 1? So the 1 gets claimed. He gets claimed by the 4. But look at your negative 2's. Do y'all see how nobody claims him? What does that mean happens at negative 2? There is a hole. The function is absolutely and 100% not continuous at negative 2 because no part of this function defines the value at x equals negative 2. It does not exist. Okay, now it says which statement is true? F is discontinuous only at negative 2. Okay, well, I think we've established that it is discontinuous at negative 2, but I don't know about the word only. So he's a yes. I just need to see what else happens here. F is discontinuous at x equals 1. Okay, well, this is the 1. This is where they're going to connect. So what I need to do is I need to see, well, this function obviously is going to be at 4 at 1. Now I need to see where this guy is at 1. Well, if you plug a 1 in, he's going to be at 5. So if he's at 4 at 1 and he's at 5 at 1, they're not going to connect, which means they're discontinuous. So he's true. Okay, now this says if f of negative 2 is defined to be 4, then it will be continuous everywhere. Well, that's true if f of negative 2 is defined to be 4. That's true. That part will be continuous. But this part will not still be continuous. So I'm not going to be continuous everywhere. It fixes this problem. It doesn't fix this problem down here. So he's out. F is continuous everywhere? Absolutely not. We already know 2 places where it's not continuous. Then this one swoops in and saves the day and says F is discontinuous here, and that is true. Okay, the next one we're going to go to is Barron's 3. Okay, so now we're on Barron's exam number 3. We're going to look at number 1 and number 2. Okay, so the limit of x, and it's got these brackets around it. And it even says, which I don't see them doing on the exam, it tells you that this is the greatest integer. Okay, so if you guys will remember, sometimes it looks like this. It's the greatest integer function. So what it is every single decimal that I could give you, it's the greatest integer that's in that decimal. So 2 would be 2, 2.1 would be 2, 2.7 would be 2, 2.9 would be 2, 3 would be 3. And all the decimals between 3 and 4 would trump down to 3. And then you'd go to 4. So it looks like a step function. So, and we're approaching 2. So all the decimals in between 0 and 1 are going to trump to 0. But then as soon as you hit 1, it's going to go up to 1 because 1 is the greatest integer that's in 1. And then all the decimals that are in between 0 or 1 and 2 are going to go to 1 because this would be like 1.1, 1.2, 1.7, 1.9. All those would go to 1. So all of these decimals in here go to 1. But then when you hit 2, it's going to pop up to 2. Okay, and I want the limit as x approaches 2. Well, here's 2. Well, if we fly in from the right and fly in from the left, we're headed to 2 different numbers. Flying from the right, we're headed to 2. But flying from the left, and we're headed to 1. So the limit overall does not exist. Now, you want to fly in, like if I did the limit as x approaches 2 from the right, that's a 2. The limit as x approaches 2 from the left, that'd be a 1. But the limit from both sides does not exist. Okay, now we're going to look at number 2. Again, I could try to make this fit that f prime of x limit as h approaches 0. I could try to use that, and it would completely work. Your f of x is sine. What you're plugging in is pi over 2. The reason this is a -1, if you'll remember, or look at your formula sheet, that is f of x plus h. So this piece right here is just a 1, covered it up, because if your function is sine of x and what you're plugging in is pi over 2, remember pi over 2 is up here, and sine of this value is a 1. So they've just gone ahead and evaluated it. So sometimes that can look a little tricky. If you can see and use this, then there's your f of x. So f prime would be cosine. So then I would just need to do cosine of pi over 2, which is 0, which is your answer. So you can do it that way, and that's totally fine. Or you can Hopital. So if I take the derivative of the top, that's going to be cosine of all the inside stuff times the derivative of the inside stuff. Well, the derivative of pi over 2 is 0, and the derivative of h is 1. And then minus the derivative of 1 is 0 over the derivative of h is 1. So really, I just have this. And then I can reevaluate my limit as h goes to 0 because I don't have a denominator anymore like that. That was bad. And if I plug in a 0 in here, then I just have cosine of pi over 2, which again is 0. So you can use the definition of a limit, or you can L'Hopital the top and the bottom and do it that way. But again, like we've already done 2 or 3 of these are showing up a lot, so make sure you're really good on those, and you'll have some to practice in your homework. All right, we are now jumping to number 17. Okay, suppose f of x equals that, x can't equal 0, and f of 0 is 1. Again, because if x was 0, we would have a 0 in our denominator. So then they have defined f of 0 separately as a 1, which is most likely going to plug that hole or give it a value that would not make it continuous, and that's what we're trying to figure out. Okay, which of the following statements are true? F of x is defined at x equals 0. Absolutely, right there. There it is. They defined it. 100%. The limit as x approaches 0 exists. Well, the limit, it has nothing to do with where we're defined. The limit is what is it approaching from the right and from the left. So what we need to do is we need to figure out what happens at x equals 0. Is this removable or is this an asymptote? To find an asymptote, you set the bottom equal to 0 and solve it, and that would give me x equals 0. But if it's a removable hole, it will cancel. So this is a hole, not an asymptote. Because it's a hole, then I know that the limit exists, because whatever this function does at 1, it's just going to have a hole, but the limit is going to exist on both sides. Now, make sure you know the difference between an asymptote and a hole. If you factor and something cancels, it's a hole. If nothing factors and nothing cancels, Well, it can factor all it wants to. If nothing cancels, and you set the bottom equal to 0 and solve it, that's an asymptote. If it's just a hole, the limit still exists. Now, number 3 is a great question because number 3 says, okay, you're defined. And number 2 says, all right, you've got a limit, you exist. But number 3 says, okay, let's take it one step farther. Are you continuous? So guys, what this is saying is, all right, I understand you got a hole. Now I want to know, does this plug the hole or does it plug it somewhere else? So we need to figure out what happens at 0. If I let that go, this is now what I'm left with. If I look at the limit as x goes to 0, plug a 0 in there, I get a 1. So at 0, that's where we're headed. It doesn't happen because if I was 0, it would make the denominator 0 and bad things happen. But the limit is headed towards 1. So here's what we've got. Whatever this function does, whatever it does. But as you head to 0, I know that this function is headed towards the y value of 1. Then it came in here with this piece and said, all right, I hereby declare that f of 0 equals 1. So when x is 0, I hereby declare that y is 1. So it just plugged that hole. So this number and this number are the same. So plug the hole. So yes, I am continuous. There are lots of problems that are asking about, and they're in this format that we hate, where they give you Roman number 1, 2, and 3, and then all your multiple choices are different combinations of those. There are lots of them about something being defined, something about a limit, and something being continuous. Remember, the limit can exist and it not be continuous. If I didn't have this, then number 2 is still true. And if I had this, let's say it was 2, then this would be true because the limit exists, because it's a hole, not an asymptote. This is defined because they defined it. This is now not true because the limit as we head to 0 is a 1, and they have now just plugged it at 2. So it would now be plugged up here, and this would now be an open circle. So it would not be continuous because I still have a hole in the middle of this spaghetti string of a function. All right, now we're headed to number 20. Okay, this is the limit as x approaches 3. If we plugged in a 3, bad things happen, but you can really automatically see that the bottom factors, that cancels, but that takes out x being a negative 3. So I now have this. Nope. Sorry. Why I wrote that bar. And if you plug in a 3, bad things still happen in your denominator. So this is absolutely an asymptote. This was a hole. So the limit would have still existed at a negative 3. But at 3, no, this is an asymptote. And when it's a single power, they always go in opposite directions. And I don't know, let's see, horizontal asymptotes, bottom's bigger. So he's going to do something like this. So they're going to be headed in 2 different directions. So non-existent as the limit approaches 3. So be careful with the 3's. Don't say that, ooh, those cancel, so now we're okay. That's a positive 3. This takes out the negative 3. That's the hole. This at 3 is an asymptote. And again, make sure you know the difference between a hole and an asymptote. All right, so that was 20. Now we're headed to 27. Okay, and this is the limit as x approaches infinity. This is going to be, okay, so as x approaches infinity, it's not like you have to worry about holes or asymptotes because, number one, nothing factors. Nothing would make the denominator 0 because you're squaring it and multiplying it by 4 and adding 9, so it will always be greater than 0. You're headed to infinity. So factoring and canceling, finding a hole, finding an asymptote, none of that stuff works. So when you're kind of just super algebraic, then you really just want to go Hopital's rule. So I'm just going to take the derivative of the top. So that would be a 0, and then a 1, and then a minus 6x, and then an 8x, and the 9's going to go. And again, if I'm still going to infinity, I'm still getting a infinity over infinity. So I'm going to go Hopital again. So it's going to be a negative 6 over an 8. Now I don't have any x's, so it doesn't matter where you're headed. But my, where did I get a 6 from? Hold on, back up. That's a 2. Sorry, I thought that was a 3. That's a 2. So that would be 4x, and then a negative 4, which gives you a negative 1/2. Okay, so the next, we're going to go look at Princeton, the first one. Okay, and in Princeton, on test number 1, we're going to start with number 4, and you need to get your hands on your formula sheet. Okay, so number 4, I'm doing the limit as x approaches 0. If I plug a 0 in, I can do sine of 0 squared. That's no problem, but I cannot have a 0 in the denominator. You need to know those limits that are on your formula sheet so well that when you look at this, it makes you think of, hold on, it makes you think of this guy. Okay, I'm really close to having that, but I need this and this to be the same, and that's not the case here. Now, I can't change my ofs, so I'm stuck with that x squared, but I can multiply him by an x. But I can't just multiply him by an x. I have to multiply by x over x. That's what makes it legal. So what I'm going to do is I'm going to have this x on top, and then this x times this x gives me x squared. Now, this x right here is that x right there. So take a second and make sure you see what I did. I have to multiply by x over x because that equals 1. That makes it legal. My top x is sitting here. My other x went in here to make that guy squared. But now I can do this. Well, this x right here is just multiplication. And if you want to, you can, I mean, you certainly don't have to write it, but you can think about it. This piece right here follows that and goes to 1. So this is 1 times, well, this guy is no big deal. I can just plug in a 0. There are no denominators. I don't have to worry about anything. I just plug a 0 in. That gives me 0. And 0 times 1 is 0. They don't all go to 0. In fact, very few of them do. Make sure that you really understand that process because Princeton really likes those trig formulas. Okay, the next one we're going to go to is number 14. Number 14 has nothing to do with limits. He is a sine function, and I want the period. It just didn't fit anywhere else, so I decided to throw it in with limits. Okay, this is going to take you back to pre-cal. You got to remember, this is your amp. This is a vertical shift. That was your horizontal shift. I'm interested in the period. The period is how long it takes for it to do a complete cycle. And the period for sine and cosine are both 2 pi. The period for tangent and cotangent are pi. But you can stretch or shrink the period based on whatever b is. If you'll remember, the period is 2 pi over b. b is the coefficient in the of on the x. So if I look at this guy and clean him up a little bit, and then you don't have to do this, but just to see it, there's your amp, there's a flip, there's a vertical shift 2, here's your horizontal shift, so you'd set that equal to 0 and solve it. This is the guy I'm interested in right here. That's my b. So I'm going to do 2 pi over 4. Bojangles, pi's cancel, gives me 8. Okay, and now we're headed to number 15, which is right below. Okay, I've got a piecewise function. It says for all real numbers x, which of the following must be true? It says f is continuous everywhere, f is differentiable everywhere, f has a local min at x equals -2. Okay, so we're going to kind of play the multiple choice game a little bit on number 3, but let's work out 1 and 2 real quick. He's pretty easy. Continuous just means that these two pieces can't have a break at 2. That's where we chop them at 2. So even though they're two different functions, if it's continuous, those two functions have to meet. So if I can find out where he is at 2, let's see, that'd be a 9. And where he is at 2, that'd be 14 minus 5, that'd be a 9. So they're both at 9, so they meet. So we are continuous. So I need an answer that has a 1 in it, so I know it's not C. Differentiable. Okay, and this is something that I'm sure you've forgotten. Differentiable everywhere. What that means is that you need to find the derivative of the first guy. Well, find the derivative of the first guy at 2, and it needs to equal the derivative of the other guy at 2. The derivatives need to be equal at the break. So if I take the derivative of the first guy and the derivative of the second guy, and then plug in a 2, well, that'd be a 4. He'd still be a 7. They're not equal, so this is false. I need these two numbers to be equal for it to be differentiable everywhere. Okay, so everybody memorize that right now. Differentiable everywhere means take their derivatives of each one, set them equal to each other at the break, and see if they're equal. Okay, so that means 2 can't be in my answer. Well, he has a 2, and so does he, so it needs to be A. F of x having a local minimum, that has to do with curve sketching and maxes and mins and the table and the chart, which we'll review later. Okay, now we're going to jump to number 23. So I want the limit as x approaches 0. So if I plug in a 0, bad things happen. Now make sure that you don't overlook the 4 that's in the. Okay, so see the 4. He's just kind of hanging out, just kind of extra. I see this. Oh, I can take a sign out. Let's try that. Let's look at that. I've got a 4. And then I'm just going to take a sign out. I shouldn't lose my X. Okay, and the limit's headed to 0. All right, think about those formulas. You've got 1, that's the limit as x goes to 0 of sine of x over x equals 1. Then you've got 1 that's 1 minus cosine x over x, and that equals 0. Okay, so guys, I'm going to pull this apart and give each one an x. This is multiplication. So what I'm going to do, don't lose your 4, is I'm going to have sine of x over x times cosine of x minus 1 over x. So everybody see what I've done? The limit as x goes to 0. So this guy right here goes to 1. There's your 4. This is all multiplication. Now this guy is close to this, but not. I need to pull the negative 1 out of my back pocket. I'm just going to throw it down on my 4. That allows me to flip this around and make it 1 minus cosine of x. Now I have this, and that goes to 0. The answer is 0 because the 0 wipes everything else out. But again, make sure you understand the math in these limit formulas, and make sure you understand how important it is that you know these special limits because they pop up. All right, the next one, that was 23, we're going to go to 29. Okay, 29. This is a classic and you have to have that memorized, and you have to be able to see it and pick it out. I mean, this is just perfect. F of x is going to be tangent of x. X, what's being plugged in is pi over 6. But I don't plug pi over 6 into tangent. Remember, this is the definition of a derivative. So I need to find the derivative of tangent, which is secant squared. And now I need to find that at pi over 6. Okay, pi over 6 is here. Is that ugly pretty or pretty ugly? Ugly pretty. Secant is cosine flipped, and he's got to be squared. So 4 over 3. Okay, the next one we're going to do is number 35. I tried to pull problems that I knew you might struggle with or have questions about or that have little hiccups in them, and then I tried to leave all the really straightforward ones for y'all to do for homework. Okay, number 35. This is, I know it's blurry, x approaches 0. Okay, if I just plug in a 0, the denominator goes to 0, and that's bad. This does not fit the f of x plus h in any way, shape, or form. I cannot factor it and cancel and look for holes or asymptotes. I can't do any of that, so I'm going La Hopital. Now, to do La Hopital, I have to remember how to take the derivative of 3 to the something. So to take the derivative of 3 to the something, it's 3 to the something, leave it alone, times the derivative of the up times ln of the base. And this is your base, or this is your base. A lot of people forget that part. We did it a lot with e's, and if it was e to the sine of x, then it would be e to the sine of x times cosine of x times ln of e, which is 1, so we'd leave that part off. But this one, because it's a 3, you have to have that 3. Over, and the derivative of x is 1. So yay, now we've solved the bottom's going to 0 part. So now I can reevaluate my limit. Well, 3 sine of 0 times cosine of 0 times ln of 3. Okay, sine of 0. That's here. That's 1, 0. So sine of 0 is 0. Now be careful. Sine of 0 is 0. So it doesn't make this 0. It makes this 0. So 3 to the 0 times cosine of 0 is 1. Ln of 3. 3 to the 0, anything to the 0 power is 1. So this is 1 times ln of 3. So it's ln of 3. So nice little review of a derivative rule there. All right, now we're headed to number 43. And this is a really good one that pops up a lot. Okay. It says if the function is differentiable, okay, you got to remember what that means, at f of x, then find a. Okay. Differentiable, number 1, means you're continuous. So you have to be continuous, and then you have to be differentiable. Being differentiable implies that you're continuous. I need both of these pieces of information. Continuous means that this guy equals this guy at the break, and the break is at 1. So it means that this equals this. Well, I have an A, a B, and an X. Like, that's crazy. But it's supposed to happen, it's supposed to be true at the break, which is 1. So I'm going to plug 1s in for all my X's because I'm interested in what happens at 1. So that would be A minus 6 equals B plus 4. And then I'm just going to clean this up. I'm going to leave my A. I'm going to subtract my B over, and I'm going to add my 6 over here. So this is the guy right here. Okay, so I've done the continuous part. It got me to there. Now the differentiable, do you remember, it was f prime of the first one has to equal f prime of the second one at 1, at the break. So I'm going to take the derivative of the top one. X squared minus, is that a plain old 6? Yeah, 6 equals, okay, derivative, 2bx plus 0. Okay, so this is the derivative equals the derivative, but it needs to happen at once. I'm going to plug a 1 in for my x, so 3a minus 6 equals 2b. Now I'm going to try to make it look like the other guy. I'm going to have my a, I'm going to subtract my b over, and I'm going to add my 6 over. Okay, so this is the guy. Being differentiable got me that guy. Make sure you understand both. Now I'm going to take this, and I'm going all the way back to Math 1. But you did it in Math 2, you did it in Math 3, and we did it in Pre-Cal. We're going to do a system. So a minus b equals 10. 3a minus 2b equals 6. Go back and ask who it wants you to find a. Guys, if it wants you to find a, then we're going to try to get b to cancel. So what I'm going to do is I'm going to multiply the top equation by negative 2, because that's going to make this a positive 2b, which is then going to cancel with that negative 2b. So negative 2a plus 2b equals negative 20. I'm bringing the other guy down. Those cancel. This is called elimination because something just eliminated. That's going to give me a positive a, and that's going to give me a negative 14. So a equals a negative 14. Okay, again, differentiable implies that you are continuous. Continuous means that this function equals this function at the break. So set them equal to each other, plug in a 1, clean it up. Differentiable means the derivative equals the derivative at the break. So take the derivative, set it equal to the derivative, plug in your 1, clean it up. Then I put both those two things together, and then you have to get somebody to cancel. There are a couple of these on your homework that you get to practice. So make sure this is soaked in and make sure you knock those two out. All right, the next one we're going to is Princeton 2, and we're headed to number 7. Okay, it says find K so that that is continuous. Well, if it's continuous, then the first function equals the second function when x is 4. So let's see, I'm going to clean this up like that factors, and this cancels. So I really just have this. Well, that's nice. And I want it to happen at the break, which is 4. So K needs to be 8. Again, that's not hard math. It's making sure that you understand what continuous means, and I hope that you see that we've done enough of these from Barron and from Princeton to know that this is really important. All right, now we're headed to number 15. Okay, number 15. It's not a factor and cancel. It's not a definition of a derivative with a limit formula. This is just a good old Hopital. Remember, you're not doing a low-D high, high-D low. You're literally just taking the derivative of the top, which is going to be a product rule, over the derivative of the bottom, and then reevaluate your limit. So I'm going to take the derivative of the x, leave that guy. Then I'm going to leave the x, and then I'm going to take the derivative of the second guy. So that's leave it, derivative of the up times ln of the base. And then the bottom is going to be, let's see, leave it, derivative of the up, ln of the base, and then minus 0. And let's see, I'm going to 0. Oh, and the reason I had to do this is because if you plug a 0 in here, that would be 2 to the 0, which would be 1, and 1 minus 1, which would be 0, which is bad. So now let's try it. Let's see, if I plug in a 0, if I plug in a 0 there, that's going to make that a 1. A 0 here is going to wipe out all of that, so I don't even care what the rest of it is. It's just a 0. And then the bottom's going to be 2 to the 0, which would be 1 times ln of 2, so 1 over ln of 2. Again, I hope this is helping you brush up on your derivatives. All right, now we're headed to number 24, which is a good one. Okay. Let's see, that's tangent cubed of 2x over x cubed. Limit as x goes to 0, so if you plug a 0 in the bottom, that's bad. It's not the definition of a derivative. I'm going to try to make it, I'm going to try to make it using one of those trig limits. So I'm going to take tangent, and I'm going to put them in terms of sine and cosine, because all the trig limits that we're supposed to memorize are in terms of sine and cosine. So I'm going sine cubed 2x over x cubed cosine cubed 2x. So all I did was take him and write him in terms of sine cubed and cosine cubed, and this guy's just chilling right there. Okay, so now let's see. Let's try to pull this sucker apart and see if I can create okay. Now let's see. I need a 2 right here. But he's being cubed. So if I need a 2 as a part of this, if I put a 2 here, I have to balance it with an 8 because 2 cubed is 8. So if I put a 2 here to make the ofs the same, make sure you understand that. I put a 2 here so that my ofs are the same, but he's being cubed, so I have to balance it with an 8. So it's like I multiplied it by 8 over 8, but I wrote this one as a 2 cubed instead of an 8. This limit goes to 1. Then I have my 8. This isn't anything. The one with a cosine is like a 1 minus cosine on the top. But remember, I'm headed to 0. Well, if I plug in a 0 here, that's going to make this a 0. Well, cosine of 0 is 1. And then 1 cubed is 1. So that's all good. Answer's 8. All right, now we're headed to Princeton 3, number 15. Okay, and this limit is headed towards infinity with ln's and logs. I'm going La Hopital. Okay, so the limit, so let's take the derivative. So the derivative of the of over the of times natural log of the base. Well, this one's base is e, so that's going to go away. Over a log, derivative of the of over the of times natural log of the base. That one doesn't go away because he's not an e. I'm going to Bojangles. Okay, and then if I plug in an infinity, he's going to go to infinity, and so is he. Doesn't help me at all, so I'm going La Hopital again on this guy. So let's see, derivative of the x, leave it, plus, well, I could do a product rule on this, but let's look at this. Let me keep going. Derivative of him is a 1, then leave it, ln of 2, and then I leave him, and then I take the derivative of ln of 2. That's a constant, so the derivative of that's going to be 0. Over derivative of the bottom is a 1. So all I have is ln of 2, which has no variables in it whatsoever. So I don't even have to worry about going to infinity. The other thing you could have thought of is this is like ln of 2 times x. This is sort of just like a coefficient. So if you're going to La Hopital this, the derivative of this is just going to be ln of 2. Think about it. If you had 5x, the derivative of that would just be 5. Well, I have ln of 2x, so the derivative of that would just be ln of 2. Or you could do product rule. Either way. But that's a Hopital twice. All right, so that was number 15. Now we're headed to 24. Okay, and this is a good one. Write small. Okay, here's what I'm going to do. I'm headed to 0. Sine of 0 is 0, so this is bad. I'm going to pull it apart. And it might be good just to watch this one once and then go back and write it. Okay, now I'm going to make the tangent. Okay, I'm going to Bojangles this guy. Okay. Now, if I can put those two together, I can do that sine of AX over sine of BX. And pull this guy off to the side. And this, as the limit goes to, as it goes to 0, that's going to go to 3/5. Now this guy, as the limit goes to 0, so that would be a 0. But remember, cosine of 0 is 1. So we're good there. He's a 3/5. This is still bad because if I plug in a 0 here, the bottom's going to, sine of 0 is 0. That's bad. But this is almost this one, which would be a 1. He is a 5x, which I can't change. He's a 3, which I don't need, but I can give him a 5 and give him a 5 and look at this. That's going to go to 1. And then I have this 3/5. So it's 3/5 plus 3/5, which is 6/5. That's a good one. And by good, I mean a hard pain in the butt. So again, watch it one more time, then go try to do it without listening to the video and see if you can get that one. He's a good one. Okay, now I'm going to 39. See, and 39 is easy. We can do 39. Y'all could have done 39. Okay. So you could do Hopital on this, or you could see that this is except this piece right here. First, define your f of x. That's going to be sine of x. You can already see that your f is 5 pi over 6. So why is this a 1/2? Because it's f of x. So the sine of 5 pi over 6 is a 1/2. They've just already done that part. So then you need the derivative. And that's cosine of x. And then you just need to take the derivative at 5 pi over 6. And that's ugly, pretty. I don't want cosine, so it's that one. And again, I know I'm going fast, so if you need to slow this down, if you need to go back over it 500 times, then that's what you do. Okay, the very last problem we're going to do is on the extra practice, and we're going to do number 10. Okay, let f of x equals that, and let f be continuous at 5. Then c equals, oh, it wants to know what f of 5 needs to equal so that it's continuous. So I can't plug in a 5 because the denominator will go to 0. The only thing you have here is conjugate of the top. So let's see, that's going to make the top x plus 4, inside, outside are going to cancel, and then minus 9. And you go ahead and look, that's going to give you x minus 5. On the bottom, I'm going to leave my x minus 5 out. Do not distribute it, just like we did before on that other problem, because that's going to allow those to cancel. So now I have this, and now I can see what happens at 5. If you plug a 5 in here, that would be a 9. Square root of 9 would be 3, and 3 plus 3 would be 6. So 1/6. It needs to plug in at 1/6 for it to be continuous. Okay, so I know this was a lot, but we've covered a lot. And so you need to make sure that you're good with limits and continuity and asymptotes and holes and the limit rules that you're supposed to memorize and the definition of a derivative that involves a limit. L'Hopital's rule, all these nitty-gritty details you need to make sure you're good on. make sure you do your homework, and we will check it the next class.